Estimates, like the sample mean or sample standard deviation, can change with each new sample. Understanding this fluctuation is central to developing a foundation for understanding the quality of parameter estimates. This video accompanies the discussion of variability in estimates in open intro statistics. Here we will learn about point estimates and see that point estimates are not exact. We will also have our first opportunity to quantify variability in estimates by studying the standard error of the mean. Finally, we will conclude with a summary of a few basic properties of point estimates. Suppose we want to estimate the population mean based on a sample. The most intuitive way to go about doing this is to simply take the sample mean. The sample mean is called a point estimate of the population mean. If we can only choose one value to estimate the population mean, this is our best guess. If we take a new sample and recompute the mean, we will probably not get the exact same answer that we got using the first sample dataset. Estimates generally vary from one sample to another. This sampling variation suggests our estimate may be close, but it will not be exactly equal to the parameter. Estimates are usually not exactly equal to the truth, but they get better as more data become available. We can see this by plotting a running mean from a sample of times for people finishing the 2012 Cherry Blossom 10-mile race in Washington, D.C. A running mean is a sequence of means where each mean uses one more observation in its calculation than the mean directly before it in the sequence. For example, the second mean in the sequence is the average of the first two observations, and the third in the sequence is the average of the first three. The running mean for the 10-mile race times is shown in the figure, and we can see it approaches the true population average, 94.52 minutes, as more data become available. From our first random sample, we guessed the average time it takes to run 10 miles is 95.61 minutes. Suppose we take another random sample of 100 individuals, and its mean is 95.30 minutes. Suppose we took another 93.43 minutes and another 94.16 minutes, and so on. If we do this many times, which we can only do because we have the entire population dataset, we can build up a sampling distribution for the sample mean when the sample size is 100. The sampling distribution represents the distribution of the point estimates based on samples of a fixed size from a certain population. The sampling distribution shown in the figure is unimodal and approximately symmetric. It is also centered exactly at the true population mean, mu equals 94.52. This makes sense because sample means should tend to fall around the population mean. We can see that the sample mean has some variability around the population mean, which can be quantified using the standard deviation of this distribution of sample means, 1.59 minutes. The standard deviation of the sample mean tells us how far the typical estimate is from the actual population mean, 94.52 minutes. It also describes the typical error of the point estimate, and for this reason we usually call this standard deviation the standard error, SE. Given n independent observations from a population with standard deviation sigma, the standard error of the sample mean is equal to sigma divided by the square root of n. In this video, we established a few basic properties of point estimates. First, we determined that point estimates from a sample may be used to estimate population parameters. We also determined that these point estimates are not exact. They vary from one sample to another. Lastly, we quantified the uncertainty of the sample mean using what is known as the standard error. If you learned something you found interesting, share this video with a friend and visit openintro.org for more resources.